Welcome to our last topic in the acid-base equilibria series. And this last topic is on acid-base titrations. So hopefully in General Chemistry 1, you've heard about titrations. You may have even done a hands-on lab or a simulation where you took a burette. So burette is going to be that long, skinny piece of glassware. So let's change the color for a moment. And you would add a certain amount of solution, right? So that's the burette, the long skinny piece of glassware, and you've got a solution in a beaker that you're adding to it, and that is your known solution. And it's also what we call the titrant, right? So the titrant is going to be in your burette, and then in the Erlenmeyer flask below, so I'll change the color. Let's try that. So in that flask below, you have an unknown concentration, what we call the analyte. Okay, and the whole purpose is that you slowly add your titrant to the analyte until you have a reaction that goes to completion. And usually we'll either have a pH meter that measures the pH, or we may have a pH indicator to see a color change. And whenever that reaction goes to completion, we've reached what we call the equivalence point. So even if you didn't do a hands-on lab or see a simulation, hopefully you at least worked through some problems where you were given a certain volume of a known concentration, let's say of a base in this example, and you reacted it with a known volume of the strong acid. Okay, and we won't work through this problem, but this just kind of gives you an idea. You would have the known volume and concentration of your titrant, you would have the known volume of your analyte, and you would try to find that molarity of the analyte. Again, where this HCl would be considered your analyte, and the sodium hydroxide is your titrant. Now, as you did this reaction in the lab, and as you added slowly that sodium hydroxide to the acid, as you're reacting it, and before you add the entire 35 milliliters, you would have all of the sodium hydroxide react with the hydrochloric acid, and you would have leftover hydrochloric acid that was unreacted before you reach that equivalence point. And so if you have unreacted hydrochloric acid, remember that that will, in water, form your hydronium ions. And so you would get a very acidic solution. And then, of course, as you continue to add that base, and if you went over 35 milliliters, let's say you overshot it and went to 40 milliliters, then you would have leftover unreacted sodium hydroxide because all of your hydrochloric acid would be used up. And in that case, you would have leftover hydroxide ions, and so you would have a very basic solution. Okay, so what we're going to look at in General Chemistry 2 is that we are going to look at more detail in the titration curves, and this would be where we measured the pH with a pH meter at every step of the way. Okay, and as we do that, as we increase the volume of the sodium hydroxide added, we'll measure that pH, and then at the steepest point in the middle, we'll find our equivalence point. And in General Chemistry 2, we can react a strong acid with a strong base, or we can react a weak acid with that strong base. And so we're going to see some slight differences in the curves. With a strong acid, if you have nothing but acid in the solution, of course you're going to start out at a lower pH than what you do if you have a weak acid. So that's one difference between the two curves. Now, once you add an excess amount of the sodium hydroxide at the end, so in both cases we're using sodium hydroxide, it's the same concentration, and so at the end of it we're going to have the same ending pH, because you have the same excess base left over. And so the difference is you'll see that the titration of a strong acid with a strong base is going to have a taller titration curve in comparison to that weak acid. And again, that stems from the fact that the weak acid is going to start out at a higher pH. You'll also notice a difference in the equivalence point. So if you react a strong acid and a strong base, you have nothing left over except for an inert salt and water. And so the equivalence point is going to be neutral. It should be right at 7.0. But with a weak acid, you're going to have leftover conjugate base. So the conjugate acid will react with the sodium hydroxide to form that conjugate base. And so that leftover conjugate base is going to push that pH above 7. So in words, again, we won't go through all of this, but this is just a summary of what I've been talking about. The initial state, that's before you add any of your strong base, and so your pH is going to be determined by the pure acid, whether it is a weak acid or a strong acid. Now the pre-equivalence point, that's before you reach the equivalence point, so we would be in this area here. You're going to have leftover acid that hasn't reacted with the base. So all of the base will be used up, and the leftover acid will determine your pH. Now at the equivalence point, if it's a strong acid and a strong base, then your equivalence point will be a pH of 7. If it's a weak acid with a weak base, then you'll have to use the conjugate base of that weak acid to determine the pH. And then post-equivalence, when we have went past that equivalence point and we have excess strong base, then we will use the excess strong base to determine the pH. So now we're going to work through some examples. We're going to see this play out. We'll do a strong acid and a strong base example, and then after that we'll do a weak acid and a weak base example. And we're going to look at the initial state, the pre-equivalence point, the equivalence point, and the post-equivalence point. So my suggestion when you're working out these types of problems is to first determine what is your equivalence point. At what point do you have all of the acid reacting with all of the base? And the way you do that is to look at the balanced chemical equation, find your moles of each, and find out what that equivalence point is. So let's determine the equivalence point by first writing out the reaction. We have nitric acid, HNO3, reacting with sodium hydroxide. So we've got HNO3, which is a strong acid, reacting with sodium hydroxide, a strong base. And so of course we're going to form water and the inert salt, and its outer and inner, and the other product being that sodium nitrate. Okay, with this reaction we know that everything is a 1-to-1. If you balance it out, you'll see that we didn't have any 2-to-1 ratios there. So now we can look at how many moles that we have of the known compound. We've got 50 milliliters, and this is technically of the analyte. So a lot of times we have an estimate of what we think the concentration of the analyte will be, or we can run a quick titration to get an estimate of what that is. And so once we estimate it, then we can run through the titration to figure out exactly what it is. So in this case, we're estimating that 50 milliliters of the analyte of a 0.1 molar concentration. So I can figure out the moles of nitric acid, and that's what I'm going to do. That 50 milliliters, I can rewrite it as 0.05 liters times the molar concentration of 0.1 moles per liter. And let's see, that will give us 0.005 moles, and sometimes it's helpful to keep on the outside here, I should have wrote nitric acid, and so that is moles of the nitric acid. Okay, well, if everything is a 1-to-1, if that is my moles of nitric acid, then I need exactly 0.005 moles of sodium hydroxide to react with that. So I know the moles of sodium hydroxide that I need, and I also know the concentration of the sodium hydroxide. right? So I can use moles and molarity to find the volume of sodium hydroxide at that equivalence point. So 0.005 moles times the concentration, and we want to flip that and divide by that concentration of molarity so that moles cancel out. Okay, keeping in mind that this is all for the sodium hydroxide. And so I get 0.025 liters, or 25 milliliters of sodium hydroxide. And that is at the equivalence point. Okay, now you may have been able to figure this out without having to do the math. If the numbers are not as simple, then that shows you how to do it. But of course, if we have 50 milliliters of a 0.1, then we're going to need half of the 0.2 to make that happen. And so that's how we get that 25 milliliters. But this is the longhand of how you figure that out if the numbers are not simple. So 25 milliliters is the equivalence point. So everything before the 15 milliliters will be the pre-equivalence point, and the 40 milliliters will be the post-equivalence point. And the issue is when you're doing problems like this, typically you're only given one set of milliliters instead of 4. So you're only trying to figure out in one instance, and it's helpful to know which place that you're at to determine the strategy you're going to use to get that pH. Okay, so with all that, let's start with the first example of 0 milliliters. So 0 milliliters, of course, is going to be our initial state. And therefore we've got pure acid. Okay, so if we've got pure acid, then especially a strong acid, that tells us the concentration of the hydronium ions, and it's very simple to calculate the pH there. We've got the 0.100 molar of nitric acid, and that equals the same concentration that is equal to the molarity of your hydronium ion, because it's just going to completely ionize into that hydronium ion. And so to find the pH, it will be equal to the negative log of that concentration of the strong acid. And 3 significant figures, so we'll go 3 decimal places out, and you find that it is 1.000. Okay, so simple enough. Now the second one, the 15 milliliters, that's where we're going to have to look before the equivalence point. So 15 milliliters of sodium hydroxide is before the equivalence point. And so this is when we've had some of the acid react with all of that sodium hydroxide. So we need to figure out how much sodium hydroxide that we have in 15 milliliters. And we need to figure that out in moles. So we're going to take that 15 milliliters, convert it into liters, which is 0.015, and multiply by the concentration of the sodium hydroxide to figure out how many moles of sodium hydroxide that is. And that's 0.003 moles of sodium hydroxide. Now, we have, I believe, already calculated, if we go back to the beginning, we calculated the moles of the strong acid that we have. That's that 0.005 liters times moles. And so in this case, the smaller of the two sets of moles, of course, is the sodium hydroxide. By definition, if we're before the equivalence point, it's got to be that titrant. So that is what we call our limiting reactant. And all of that sodium hydroxide will be used up reacting with the nitric acid. And so what we can do is we can subtract it out as the change. So if you were to do a full BCA table, and you could, this would be the before of the nitric acid, and then the change will be all of the sodium hydroxide reacting with 0.003 moles of the nitric acid. So that would be your change. And then the difference between the two, 0.002, is considered your after. So that's the excess. Okay, so in Gen Chem 1, sometimes we would look at the excess reactant. That is the excess reactant and how much we have left. And of course, we've already found out, because it's a strong acid, the moles of that strong acid will also be equal to the moles of the hydronium ion. And so again, we can use that in order to calculate the pH. But the issue is, before, in the first example, we had the concentration already in molarity. But what we have here is moles of the hydronium ion. So we first have to figure out what the concentration is in molarity. And so we've got to divide by the total volume of the solution. So we added 15 milliliters of sodium hydroxide to the original 50 milliliters of the analyte. Okay, so we're going to have to add that 15 milliliters plus the 50 milliliters of the analyte, so that the total volume of the two combined is 65 milliliters. Right, so that's the total volume. Okay, now we can take the moles of the hydronium ion or the moles of that strong acid and divide by the volume in liters. So 0.00200 moles divided by the 0.065 milliliters converted to liters. And you should get 0.0307. 3 significant figures. Keep that extra one. That is the molarity of the hydronium ion. Okay, because it's the same as the molarity of the strong acid. And so the last step, of course, is to take the pH, is the negative log of that concentration of hydronium ions. 3 significant figures, so we'll go 3 decimal places out, and you get 1.512. Okay, so looking back at the previous example, starting out at 0 milliliters, we were at 1, a pH of 1, and now we've increased to 1.5. So we've gotten slightly more basic. Now the next one, we're looking at 25 milliliters of sodium hydroxide added. And we already found that that is at the equivalence point. And what do we remember if we have a strong acid and a strong base that fully react? The only thing you're going to have left is an inert set of cations, anions, and water. And so you're going to get a pH of 7. Okay, and we'll keep the same number of digits out as we did before, so that'd be a pH of 7.000. So no real math to do there. If you know that you have a strong acid and a strong base, and you know that you're at the equivalence point, pH is equal to 7. Okay, and again, we'll just say you've only got water, a sodium ion, which is inert, and the nitrate ion, which is also inert because it's the conjugate of the strong acid. So our last example is 40 milliliters of sodium hydroxide added. And so of course we must be after the equivalence point. So now all of the acid has reacted with that strong base, and now we're going to have excess strong base left over. So we're kind of going to do something very similar to what we did in the second example, where we're going to create a small little BCA table, but instead of subtracting out the acid or subtracting the base from the acid, we'll subtract the acid from the base. So remember, we have to figure out how much we have in moles of everything. So to find the moles of sodium hydroxide, we'll take that 40 milliliters, convert it into liters, and multiply by the concentration of that base. And get the 0.00800 moles of sodium hydroxide. And we already know that we have the 0.005 moles of the HNO3, of the nitric acid. Okay, so all of that nitric acid is going to react. That's our limiting reactant. And so this would be the before of the sodium hydroxide, and then the change will be the 0.005 that reacts with the acid, leaving you with 0.003 moles of your sodium hydroxide. That is the after, and that is the amount of excess reactant that you have. Again, it's in moles, so if we want to do pH, we have got to get it in concentration. Also keep in mind that now, because this is the sodium hydroxide, that is equal to not the moles of the hydronium ion, but that's the moles of the hydroxide ion. So what we're going to calculate is POH first, and then we'll have to change it to pH. But we've got moles, we've got to find it in concentration. We know that we added 40 milliliters of sodium hydroxide to 50 milliliters of that acid, and so total we should have 90. So the total volume is equal to 90 milliliters. So we'll take those moles of sodium hydroxide and divide by the 90 milliliters in liters, so 0.9. And that should give us, I believe, 0.0333, repeating, concentration, and that is the concentration of the hydroxide ion. Okay, so if we take the negative log, that will give us the POH. So we'll put it down here. POH equals the negative log of that concentration, and out to 3 digits, that's 1.477. And then of course, last step, because they want the pH, we will do pH is equal to 14 minus that 1.477, and gives you a final pH of 12.523. Okay, and I'll just write here in case we can't see it. pH equals 12.523. Okay, so of course, strong base added, your pH is going to go drastically up compared to the neutral 7. So we are going to do all of this one more time. And I think it might be easier to just put that into a separate video. So in the last video, we will just go through an example of a weak acid and a strong base.